Hello and welcome to the latest webinar by BYK-Gardner. My name is John Kowalski. I'm part of the marketing team here. Effect measurements. Presenting will be Mr. Roby and Mr. Noah Morgan. Ray is our business line manager for the automotive line, and Noah is our application specialist. So we are recording this. So immediately following the presentation, you'll receive an automated message with the link. Feel free to
All right, so having some little bit of technical difficulties, but go ahead. Can anybody hear me? Let me know in the chat if you can hear me. Testing. Okay.
Perfect. Can you hear me, Noah?
Yep, I hear you.
All right. Yeah, all right. Just take it away and we'll wait for whenever John gets back.
He should pop back in shortly. Like he was mentioning, today we'll go over color and effect measurement. Specifically, we'll talk about our BYK-mac eye, what it's all capable of, some basic principles for color and effect measurement, and so forward.
Okay, are we back?
All right, welcome back.
Thank you. This is, yeah. Okay, sorry about that, folks. I don't know what happened. I just got kicked off. So, no, Ray, quit pushing. I'm just kidding. Again, welcome. We're recording this. Immediately following, you'll receive an automated link, and that you can take a look at after the fact. If you have any questions, down the road, feel free to hit reply to that. It'll come to the marketing team, and we'll route that to the technical specialist. Also, if you have any questions during the presentation, just toss them in the chat, and time permitting, we'll get to them. If for some reason we do run out of time, we'll follow up with you individually to make sure you get your questions answered. So with that, Noah, I believe you're kicking this off. So there you are, sir. It's all yours.
All right. Thank you for the wonderful introduction. So we'll go ahead and get into it here. So we'll start with the basic principles. So whenever you're viewing color or measuring color, whether it's with instrument or with your eyes, you need three important components. The first one being a light source, the second one being an object, and the third one being an observer. Without one of these, you cannot see or view color. So we'll go into how light is affected or how an object is affected by light, some different things that go on. So the first thing is our gloss, so our direct reflection on the surface. Whenever you have a light source, let's say it's coming from 45 degrees, it'll come in and hit that sample, and then it gets reflected at the opposite angle of the direction it came from. And that's typically all white light, known as our specular reflectance, which is our gloss. The second thing that happens is absorption, and so that's caused by pigments and dyes that are inside of the object. So as your light comes in, these certain selective pigments and dyes will absorb different wavelengths of light. And then the third thing that happens is your diffusion. Diffusion is what color we see the object as. So with those pigments and dyes that are selective, they'll select certain wavelengths and they'll absorb into the material. But the wavelengths that they don't absorb get diffused and reflected back out from the surface. And that's, I guess I mentioned before, it's typically what we see the surface as. Here's a great representation of all these things happening at once. So we have our incident light, which is the light from our light source coming in, and we see it contains all colors of the rainbow. It hits that surface, and then we have white light, that is our specular reflection that gets reflected at the opposite angle. We also see that we have our purple, blue, and green colors are being absorbed into the material by those selective absorption pigments. And then we have our diffused reflection, which is that light, the orange light inside of there, it's getting scattered around the material with the different orange pigments and eventually gets diffused outside of the object. And that's what we would see that color as. In this case, it's an orange solid color. So with our, with those aspects of how light affects a surface, we always have what we call a specular reflectance curve. You can think of it like the fingerprint of a color. So in the top left example here, we have a blue cup. When we look at the specular reflectance curve, which is, you can think of it, it shows all visible light. And for this example here, our blue cup, we see that our peak in the specular reflectance curve is in the blue region, which gives us that blue color. The same is true for the other examples, like the one below that one, which is the green cup. We see that the peak is in the green region, so that would be a green color. With the red, we see the same thing as well, and with the yellow too. With the yellow, there's something else going on there, but we see it's kind of even throughout most of the colors of the rainbow, but we start to see a peak in the yellow and red region, but our peak, our absolute peak, is in the yellow region, which gives us that yellow color. Like I mentioned before, our specular reflectance curve is essentially the fingerprint of a color. So you can have many variations of these curves, but they're always exact to one specific color. So, like I spoke on before with the illuminate, the object and our observer, what we can do is we can take those three aspects using instrumentation and turn them into color scales. Historically, it used to be the XYZ color scales. I believe that was originated in the 1930s. And then since then, we switched over to the LAB system. It's a much more simple to use and easy to understand color coordinate system that was introduced back in 1964. And here we have a nice representation of what that looks like. So the basic idea of how it works is we have three values. You have your L value, your A value, and your B value. Your L value stands for lightness. So at an L value of 0 is complete black, whereas an L value of 100 is white. And then we have our A-axis. Our A-axis at negative A, we are a full green, and then at positive A, we're a full red. With our B-axis at negative B, we're a blue, and then at positive B, we're a yellow. So using these coordinates, we're able to identify exactly where we are in color space. So in this example here, we have an L value of positive 58. So we look at our L scale here, our L-axis, and we find positive 58, which is right in the middle. And then we look at our A value, so it's a positive 36. So it's going to be a little more on the red side. And then lastly, we look at our B value, which is a positive 24. So it's a little bit on the yellow side. And then when we look at all those coordinates together, we see that it gives us a nice orange color. And so with the LAB system and this new color scale, we're able to identify differences between a sample and a standard. And then that is commonly referred to as our delta E. So in this case here, essentially this is the equation. So our delta E star equation is the square root of the difference in L plus the difference in A plus the difference in B squared. That all gets calculated into one value. So what's nice about the equation is instead of having to look at 3 different values to see where your differences are between your sample and your standard, our delta E equation can just make it to where we simply look at one number, which makes it a lot easier, in a quality control process. We also have what's called the LCH scale. It's on the same type of coordinate system as the LAB, but it's just another way to look at where the colors are using a different coordinate system. This system uses the same L value, so we still have the L axis from 0 to 100, from black to white. But now we have our C value, which is our chromaticity value. It just means how far you are from 0 further, and it goes further out into color space. We also have our hue angle, which starts at the positive A axis and then goes counterclockwise 360 degrees until you come back to the A axis. And with that, we're able to identify, where we are in color space, but this is more for identifying very chromatic colors. So for this example here, again, we have an L value of positive 58. So we're about a gray-like color. We have a C value of positive 44. So if we start at the 0 point and move out 44 units, we find ourselves in the orange region. So it's a pretty chromatic color already. And then we look at our hue angle. So starting at the A axis, where we see a positive 38. So we move that up 38 units or 38 degrees, and that gives us another orange color. So that's essentially how that system works there. And like the LAB system, it's recommended to, or in the delta E equation, it's recommended to switch over to LCH when you have a chroma value over 10. And so this is a representation of how to find the delta E star with using the LCH coordinates. So in this example here, we have our standard, which is the blue point. And when we find that difference value, we're going to take our chroma value of our L value of the sample. And we'll take the C value of the sample and then the H value of the sample, and we plug it into this equation. And that gives us our total difference between our standard and our sample. So just like using the LAB system, but it's slightly different in that now we're using how chromatic the color is and our hue angle. It's just another way of getting the same value. So with delta E star, I mentioned earlier, was developed in the 1960s. So it's a fairly old equation. I'm looking at it from today's point of view. And with that, there's some shortcomings. Because it's a very simple equation, you could have some issues which would cause bigger problems in a production or a quality control type of situation. And so what we're seeing here is we have our standard, and we have a sample 1 and a sample 2. They're both using the delta E star equation. So for sample 1, we see that our L values of 0.57 off, our A value is 0.57 off, and our B value is 0.57 off. So what we're seeing is we have a slight color difference, but it's across all aspects of that color. Whereas when we look at sample 2, we see that all of our difference is now just in one color component. So it's just in that A value. What that means is because this equation is weighted evenly, both of these samples are passing because our delta E star is only equaling 1. But when we look at sample 2, because it's all that change, all that difference is happening in one color component, what we're seeing is an actual visual mismatch. So sample 2 is not visually matching the standard, but when we look at it through the equation numerically, the sample would match the standard. So this is one of the shortcomings with using the delta E star equation, because it's not necessarily weighted as it could be, because our eyes aren't perfect instruments. Our eyes see differently between one another, and the simple equation isn't able to accurately depict exactly the right tolerancing for our eyes. So these are talking about the limitations again. So unacceptable color differences for larger shade colors are larger for smaller and darker shades. And the more chromatic colors have larger tolerances than pastels or neutrals. So essentially, our eyes are very sensitive to pastel colors, very achromatic colors, whereas chromatic colors, our eyes aren't as sensitive to. So you can think of, a fire engine red color would have a very high tolerance versus, a pastel red, because we'll be able to see those differences a lot clearer in those pastel colors. And this is measured values do not correlate with the visual impression. So all colors within one ellipse are perceived as the same color. So this is a great representation of the C-Lab system here. And when you look at this graph, what we're seeing is each circle has a point in the middle, and you can think of that point in the middle of each of these circles as your standard, and then the circle surrounding that is your tolerance for that. And what we're seeing is, as we're closer to pastel colors, very achromatic colors, our tolerances are very tight. But as we move out into these chromatic colors, again, our tolerances are a lot bigger, because we can't depict those differences in chromatic colors as well as we can with achromatic colors. So this just reiterates the same thing. Chromatic colors have larger tolerances than pastels or near neutrals, which is like your gray colors. Your size and the shape of the ellipse changes depending on the hue. So acceptable color differences vary from color to color. So for example, green has larger tolerances than blue. So meaning our eyes don't see every color exactly the same. And then angular dependency of the accepted values are visible as well. And just to reiterate again, when you have non-chromatic colors, so anything with a chroma less than 10, it's recommended to use the LAB system because it's more accurate to how our eyes see. But when we have chromatic colors, so anything greater than 10 values, it's recommended to use the LCH system because it can more accurately depict where you are in color space. And so to go over the tolerances again with delta E star, this is what a typical delta E star tolerance would look like. It's considered a box tolerance. And what we see here is with this box tolerance that the delta E star equation creates, we can think of our standard as directly in the middle. All the white circles are visibly passing samples, so they match the standard, whereas all the X'd out circles are visually rejected samples, so they don't match our standard. When using this box tolerance, it works sometimes, specifically for solid colors, but it works, in most cases. The issues that you run into is that we see some X's are inside of our tolerance, when they should be outside because they're visually rejected. So with that, what we can do is we can lower our tolerance to make a tighter spec. But when you do that, then you're excluding all of the acceptable matches that you found. So this kind of shows and goes over that, the delta E star equation is not always the best to use depending on where you are in color space. For pastel colors, it works perfectly fine and works great. But when you start to get to these more chromatic colors or different shades, then you might have correlation issues to your visual. This is another great example of that. So again, we have our original box tolerance in the middle here, with all of our acceptable matches being the yellow circles and everything that was visually rejected as the X'd out circle. So if we use a box tolerance system, so this is the delta E star equation, we see that with this smaller box, we're excluding a lot of visually passing samples. So, in the real world, that could mean you're throwing out, if you're rejecting all these samples here, you're throwing out a lot of product when visually they all match. So it's a big waste of money. So what you could do with the delta E star system is you can then raise your tolerance so that you're not throwing out all this product. But when you do that, now you're introducing all these visually rejected matches. So it's showing that our eyes aren't exactly perfect and don't agree with the delta E star equation, as much as it was originally thought. And so with that, new equations have been introduced and now put out elliptical tolerancing. And so what we see there is the little circle tolerance system. And what that does is we see it looks a lot better, and it correlates a lot better to our visual. So with that circle tolerance, we see that it pretty much covers most of the visually passing and acceptable samples. And it excludes all of the visually rejected samples a lot better than the delta E star equation. And this is another example of that. Again, it's an elliptical tolerance system. And so it's best because it's able to correlate better to what we see visually, which is why it's recommended for color matching and using it with these different instruments. So this is our multi-angle and flake characterization instrument, our BYK-mac eye. What's special about this instrument is it measures in 6 different angles. So we have a -15, a 15, 25, 45, 75, and 110 degree color measurement with an illumination at 45. And with that, you're able to accurately depict color flop and how the color changes depending on the angle that you're usually viewing. So any metallic colors or pearlescent pigments. It also includes sparkle characterization. So there's 3 different illumination angles for direct illumination that gets cast over your sample or whatever part you're measuring. And that's able to pick up your sparkle at these different angles. And then lastly, we have our graininess characterization. So unlike the sparkle characterization, the graininess uses a diffused illumination. So if you ever go out to your vehicle, if it's a nice sunny day and you have that direct light on your car, you'll see a lot of sparkle. Whereas if it's a very diffused lighting situation, so like an overcast day, you'll see a more graininess look. It won't be as very intense and bright as the sparkle. And so this instrument is able to accurately depict, your characterization for your graininess, your sparkle, and your color measurement at all these different angles. And this just goes over the typical tolerances. So when you have metallic colors, we typically see larger tolerances for -15, 15 degrees, 25 degrees. But at 45 degrees, we find that the tolerances are typically very tight. And the same with solid colors. With solid colors, we only have one angle that we look at because we typically don't see a change depending on the viewing angle on a solid color. So when we look at the metallics, the 45-degree angle is usually the tightest tolerance, whereas the other angles have slightly higher tolerances. The negative 15, the 15, and the 25 are higher than the 75 and the 110, typically because the 25, the 15, and the negative 15 would be looking at, you know, an extreme angle versus, you know, if you're standing next to a car and you're looking across the surface of the hood, it's typically a 75 or 110 degree angle. So it's, you know, it's something you see more visual. Whereas you're not really going to be, you know, viewing a vehicle or a metallic effect product from the negative 15 angles or the 15 angles. All right, and then for achromatic colors, it's almost the same thing. So you have a little bit of a higher tolerance for the negative 15, 15, and 25. 45 is typically the tightest here, but for achromatic, we see that our tighter tolerance is now at 75 and 110 degree angles. And then at our solid colors, we have just our 45, and it's a typical tight tolerance for that as well. All right, so this goes over some of the new and improved equations so that replace the delta E star equation. So we have delta E CMC, and we see it's a little bit more complex. And we also have our delta E DIN, which is 6175-2. Calls out, you know, differences between achromatic and chromatic colors, and so it measures in two different ways. We see these equations are now a lot more complicated. That's due to the reason that, you know, our eyes are very complex, and our eyes don't necessarily correlate exactly to delta E star. So these updates are made to these equations, which now weight colors differently depending on where they are in color space. And that's the reason for these more complex equations. All right. So with our BYK-mac eye, like I mentioned before, it measures our color at these different angles, but it also has these effect measurements, so our sparkle and our graininess. And what we see here is that we're able to break down our total difference in sparkle and our total difference in effect. And then we can combine those two differences to get our total color difference. So that includes sparkle and effect, because sparkle also plays a role in how we see color. Same with the graininess. So we see this is the equation for that to give us our total color difference. And then here we go to look at the more detailed explanation of these equations. So for our delta E total, we see that it takes into account our delta E difference in 15 degrees, 25 degrees, 45, 75, and 110, and then it divides it by those 5 angles. Now, if you use the negative 15 angle, it would take that into account, then divide it by 6. That gives us our delta E total. And then for our sparkle total, we see that it takes into account our sparkle at 15 degrees, our difference in sparkle at 45 degrees, and our difference in sparkle at 75 degrees. And then it has this a G value. And then we see down below, we have our total color difference, which includes sparkle and our color difference. And we see that's just, we take our delta E total, square, and then we take our delta sparkle total, and we put it through that equation there, and that gives us our total color difference. And so that's what we're able to do with our BYK-mac eye, in order to accurately take these special effect colors and put it through a process and find out exactly how much color difference we have between our different samples and our standards. So with that, I'll pass it over to you, Ray.
Hi, good afternoon, everyone. So we're going to talk about the effect parameters specifically now. And like Noah was saying on the previous slide, those total numbers are something that customers ask us for because they want to have pass-fail criteria that's easy for like an operator to use and that they don't have to really think about it. But the problem again with those numbers is they are a number where so many components are being rolled up into it, even though they're better than the delta E star method, they still do have some problems, and you still should look at the individual components just to make sure that you're seeing everything that's going on with the color. So for sparkle, like Noah was saying, for sunny skies, that would be direct illumination. That's where you see like the sparkle values themselves. And under cloudy skies or diffuse illumination, that's where you see this pattern on the bottom where it's like graininess. And both of these in combination give you some ideas on the flake characteristics and the size of the flakes, and also how your process is producing this material and if it's going to match the standard that you're using as your master. So for sparkle, you need, if you're looking at it inside, you would need like a spotlight to kind of mimic direct sunlight that would be outside. The angles are critical on this. There's 3 different angles that he talked about too. Those angles, depending on what's going on with your material, can give you an idea if it's material related or if it's your process related. And then the sparkle gives you an idea of the amount of the effect pigments, the size of the flakes, and also how sparkly it is or how reflective that particular flake is. For graininess, this is diffuse illumination. So if you are looking in a light booth inside, this would be diffuse illumination. You need to be at a fairly close distance because it's hard to see these far away. They kind of all merge together. But the observation angle isn't important because, again, this is diffuse illumination, so there is no angle associated with that. And then this can also give you an idea of the type of flake or the flake size. And if you have disorientation of the flakes, which I'll talk about in a little bit, this will also give you an idea if your flakes are either being sprayed too wet or too dry. It's going to give you a different graininess number. So always at BYK, we want to make sure that the numbers that you get out of our instrument correlate to what you see visually. And so this is how we did, we worked with Axo Nobel to do this, and they call it coarseness there, not graininess, but that's the only difference. And we also did the same thing with sparkle, or they call it glint for Axo, but it's the same exact approach. And basically this room is all white because it's supposed to be diffuse illumination. And then in the center, you can see a bunch of panels on a rotating platform. And then you would take different samples and compare it to them and visually assess what you think it's the closest to. So this is the anchor panel set that I was talking about that's on that rotating holder. And there are 8 anchor panels. And we use a lot of different colors because depending on the color, sometimes you can see more or less coarseness or more or less sparkle, depending on the color that you're looking at. And then people would use these anchor panels and judge where they thought it was for coarseness compared to these anchor panels. And this just kind of shows you what the anchor panels look like. And what we figured out was for graininess and for sparkle, there really was no correlation between the two. They're independent parameters. And also, there was a very high correlation between all the observers, over 90%, which is really good for a visual study. And the most important part from the study was that most people can see a difference in graininess or sparkle of 0.5 units. So the reason that we developed sparkle and graininess was there's sometimes when you are looking at a color harmony on a car or a refrigerator or something, and your color actually looks okay, but there's something not correct when you're looking at it. And this is why you needed to have instruments that can measure the effect pigments in the coating also. So now our goal when we developed the instrument was to have multi-angle color, plus we wanted to have the flake characterization. And it's really important because there's so many different flakes on the market. Now they're starting to coat them with different materials. Now glass beads are becoming popular and everyone's looking for the most interesting new effect pigment possible. So there's so many different flakes and different types of effect pigments that it's really hard to be able to figure out what the problem is when you're looking at the harmony on a vehicle. So this is how we measure the sparkle and the graininess. There's 3 different illuminations for sparkle at 3 different angles. So there's the 15 for sparkle, the 45 for sparkle, and the 75 for sparkle. And then in the instrument, you'll see like a white circle or half circle in the bottom of the instrument, and that's where we get the diffuse illumination. So the 3 different illuminations are important because depending on how you're looking at the vehicle, you're going to see different angles for the sparkle. These are the pictures that if anyone ever wanted to see pictures, there's a little program that we have where you can take the pictures and you can save them to your computer and look at the different pictures. But in this example, we're looking at the Sparkle 15, and there's 2 different flake combinations, 40 and 60% for a metallic flake, and then 60-40% is the second set that you see. And on the top for the Sparkle 15, you can really see a difference in those 2 pictures, hopefully on your screen also. And that's what the instrument is using to get the numbers for sparkle and graininess. The bottom is an example of graininess, and you can also see a difference there. So sparkle has 2 components, sparkle area and sparkle intensity. Sparkle area is how much of that panel, when we take the picture of that area, is actually sparkling. And sparkle intensity is how bright that flashback is to your eye. So the intensity of that pigment. And these 2 things are important. So if you just look at delta sparkle for, say, the 15, that's just going to give you like a delta E number. But you really need to break it down into sparkle area and sparkle intensity to figure out what's actually happening with those effect pigments. And again, I talked about this before. There's so many different flakes, and these all change how it's going to look when you add it to a coating system. So it's important that you have a way to measure these because it's going to change how it affects or appears to you, and also the harmony on whatever you're matching. So when we talk about the different flake sizes, people ask us, what's the best size flake? And it's not so much that, it's kind of like, what are you trying to accomplish? So if you have coarse pigments, they're brighter, you get higher sparkle, and you have better flop characteristics. But with coarse pigments, because the flake size is so large, sometimes they're not overlapping or they're not laying down flat. But with fine pigments, you can get better hiding capabilities of your material. And this just shows you an example of good orientation and a poor orientation. So you really want your flakes to be laying down flat against the surface of your substrate, and not like the second picture on the right side where they're all kind of at different angles. So you're going to see just different flake. It could look like it's standing up or sparkly on that angle. And really, you don't want to see sparkle on like a flop angle. And also it can help, or it can cause you to have bad hiding power because the flakes are orientated differently, and you may be able to see through to your primer with the orientation of your flakes being incorrect. And this just is a picture of what poor orientation looks like and good orientation looks like. And again, with the poor orientation picture on the left side, you have gaps in your material where you're actually seeing through to substrate, which you do not want. You really want the picture on the right where everything's laying down and it's covering up your primer and there's no spaces or gaps within that material. So for the tolerancing for this, it's kind of like what Noah was talking about with color space. Now we have sparkle space. And basically, if the like colored lines are sparkle grade lines, and we just use these for tolerancing. We don't use these when we're matching materials. But if you go up or down one sparkle grade, you're going to be able to see that difference. And if you go left to right a whole unit, you're going to be able to see that difference. And most of the time, we just use the settings in Smart Chart that are kind of the default settings, because those seem to work for most colors. But there are times when we do have to adjust the tolerancing to accommodate for like very, very big flake, like bass boat flake size, like those we have to adjust the tolerancing, because you can change the concentration of those pigments quite a bit before you see a difference visually. So those need to be opened up. And then there are some pigments that we have to make the tolerancing tighter. So here's just a couple examples of when you change this, what it does to the ellipse. And this is just like what we do with Delta CMC or Delta 2000. You can change these different specifications, and it's going to give you a different size and shape of the ellipse. But the one on the far right is 3:1, and that's what we normally use. And that's the default settings in Smart Chart. And then graininess is one-dimensional. So 0 technically would be a solid, but there are some pigments on the market now, even though they're a solid color, you do see some graininess on those panels. So just be aware of that. And also, if you have excessive amounts of dirt or something in your solid panel, that will also show up under this graininess number. But it goes from 0 to 15. And again, it's one-dimensional. So in the beginning, when I started talking, we talked about the visual difference that you can see, which is 0.5. So for this color, the color numbers look pretty good. I would think that this color, for just color, you would expect this to match very well. But when we look at the sparkle numbers, especially the sparkle 15 and the graininess, there is a huge difference. 1.3 for the dark gray fine panel and 6.9 for the dark gray coarse panel. And we were talking about, you can see a difference of 0.5. So you're going to see this difference, and it is not going to look like the same color when you put these two panels next to each other. And that's what we mean by significant. So you can see this difference, even though the color numbers themselves look okay, it's really the effect pigment that is making this not look harmonious on the vehicle. So when we developed sparkle, one of the biggest OEMs that wanted us to have sparkle was BMW, because what was happening They would match a color with a cerulean pigment, which is very, very sparkly and also expensive. And then some suppliers maybe would change it to a mica because a mica would be cheaper, but the sparkle on a mica will never be as intense as the sparkle on a cerulean. So here's two panels. The one on the left is the mica panel, and the one on the right is the cerulean panel. And you can really see a difference between these two panels, but the color itself looks pretty good, but this flake is definitely different. So, and these two panels, just for color, these color numbers look really good. So you wouldn't think there's an issue with color. But when we look at the sparkle numbers, the cerulean is definitely much more intense than the mica panel. And even if we increase the concentration of the mica in this panel, we just increase the area because the area is going across the x-axis and the sparkle is on the y-axis. We just increase the concentration, so the area that's sparkling, but we never can increase the sparkle intensity because that's inherent in that pigment itself. And when we increase the concentration from 0.3 of the mica to 0.75 of the mica, now we've completely ruined our color position because we've changed things by adding more and more mica, even though we're not getting the intensity that we wanted. And here this is just everything that goes into your overall color perception. So there's coarseness or graininess, there's glints or sparkle. You have multiple color pigments that are in there. You also have like your base color, and all this stuff ends up going into the final product, which is what we see. So here's a little troubleshooting guide that we put together. So graininess can be either formulation variation or it can be how you're applying the material. The Sparkle 15 in over 90% of the issues that we've seen are related to the actual material itself. So if you're using, like I showed you, the mica or the cerulean, it's really going to change on the 15 angle. If you have bigger or smaller flakes, again, it's going to affect the 15 angle over the other angles. And then the Sparkle 75 normally is related to the application variation. So if I apply something wetter or drier, if I use bells or guns, if I have overspray on my parts, stuff like that can affect my sparkle flash off times. If I have my clear coat is actually intermingling with my base coat, that can affect my Sparkle 75 too. So there's a lot of application variations that can affect your Sparkle 75. And we're always more than happy to take a look at the data and talk to you about your process to see if we can figure out, what's actually affecting the Sparkle 75, since it is an application issue. And then just to summarize one more time, so the instrument does the -15 through the 110 angle, so all 6 angles. The -15 angle, normally we use that for color shifting pigment. So if I go from like a red to a blue in a color, you need the -15 angle to see that change. And also sometimes there's some mica pigments that also color shift, maybe from yellow to blue or something. You'd also need the -15 for those colors. And then the sparkle characterization with direct illumination at the 15, 45, and 75. And then the graininess with diffuse illumination is everything that the instrument measures. And we think this gives you a really good idea of the overall appearance of the color and the effect pigments in one instrument so that you can measure everything that you need and get really good color harmony. So thank you. And we're here to answer questions now. So back to John.
Yeah, nicely done, Ray and Noah. Thank you very much for your input and expertise here. like Ray mentioned, if you have questions, toss them in the chat box. I think it's in the bottom right-hand corner of your screen. We have a few minutes left to help out in any way we can. We do have a question here. Is an aluminum or an effect flake, does it have gloss or light absorption?
It could have any of it.
Okay, can have either. Okay.
It could have either, because it'll absorb sometimes some colors and then reflect other colors. So yeah, either or it could be.
Okay.
It just depends on how that material is made and what the coating is on it and things like that. And the different types of flakes can be different too. So yes,
Okay.
both.
Sounds good. I hope that helps out, Christian. If you need us to elaborate or if you're going through a certain challenge at your facility, just jot it down in the chat and we can get into the details here. While we're waiting for some other questions, Ray and Noah, when are there certain things you guys hear in working with customers? Kind of the same thing over and over, that someone's doing something, I want to say wrong or in a different way where they're not getting consistent measurements over time. I guess I'm just looking for, are there basic tips that you can provide our audience with?
So
As I get into,
yeah, because the instrument is directional illumination, it really affects how you orientate the instrument when you measure.
okay.
For automotive, I always try to measure in the position the part would be on the vehicle. So in this picture, if you can see up here, there's 2 LED green lights. That's where the light source is coming from. Also on the bottom, there's an arrow that shows you where the light source is coming from. So if you're measuring like in car position, you'd always want those the green LEDs to be facing like it would be where the sun would be coming when you measure the part, because that's what you're going to see when you build the car up. And that's the angle that you need to measure. So my biggest thing that I have to always make sure I remember to tell people is that since it's directional illumination, you really need to make sure you have the instrument orientated correctly. Because if you spin it 90 degrees or 45 degrees, you're going to get a totally different answer. So it's very important.
Yeah. Now, and something like that, as basic as that is, a lot of plants that run in multiple shifts, or even, they have multiple plants and multiple suppliers. Is it best to document this is the correct procedure to do that? So when you do get the measurements and the data, it is an apples to apples comparison.
Yes. And
assuming they're doing it correctly.
Right. Yes. But I've seen where I've gotten data from an OEM plant where they said, oh, my first and second shift, there's something totally different. And it turned out it was just the direction of measurement, because the second shift guy might have been new and didn't know, and no one explained it. So it really can cause havoc at the OEM level and for suppliers too.
Gotcha. So definitely nail down that process. Are there other things that you both see in working with customers, that you could share with the audience here that could help them out?
I think the biggest thing is that for sparkle, if you're not measuring it, then you can, like I said, you can have good color measurements, but if you're not measuring sparkle, there's a lot of times when we're at color harmonies and someone says it's just not sparkly enough, but they can't tell you what to do about it. So if you measure these angles, it really helps too.
Okay, because correct me if I'm wrong, and you can definitely elaborate, because the different angles, then if there's an issue, the angles will kind of point you to that solution or where the challenge is to make corrective actions. Is that right?
Yes, correct. Like that little troubleshooting guy that I showed before.
Yeah. Where is that? Here it is.
Yeah, that one. This really
nice.
helps you when you're trying to use the data to find out things. And the other thing is, like I said, if the delta sparkle is out, you really want to look at sparkle intensity and sparkle area to see what's actually happening.
Nice.
I
Gotcha.
think Noah has a comment, so I'll let him go. Go ahead, Noah.
Yeah, I was just going to mention, something I always see is people comparing measurements, with a solid color instrument and then using a BYK-mac.
Yeah.
And the issue with that is, again, the BYK-mac is measuring with light coming from a linear direction, so it's just one single direction, whereas our solid color instruments measure with circumferential illumination, meaning the light's coming from all angles. So to kind of reiterate what Ray was saying is, depending on the angle or the orientation of the BYK-mac to your material or your sample, you could get a very different result. And especially when comparing to, a solid color instrument with that circumferential lighting, because the illumination is not exactly the same. Your measurements won't be exactly the same, but typically they'll be pretty close to one another.
And the solid color instruments work great, like on interior, perfect because of that circumferential illumination, but not so great for metallics or mica coats. So you really need to use the BYK-mac for that stuff.
Gotcha. Understood. And I think Ray mentioned earlier too, if you're having challenges, if you'd like to talk with Noah Ray, one of our technical specialists in the field, just to review your color program, what's going on, how things are working, look at your reporting. We're more than happy to do that and provide any recommendations to help, make some corrective actions. I think we're about out of time. Like I said, if someone has a question after the fact, just hit reply to any of those marketing messages. It'll come to my team here, and we can route it to Noah, Ray, or the technical specialist you need or are in your region. Any final words, either of you two? You covered a lot of territory here.
Can you hear me?
Yeah.
Okay. But now I lost my point.
That's okay. We'll cover it in the next webinar.
Yeah, no problem.
All right. Well, thank you, both of you, Ray and Noah. Really appreciate your time and expertise. Thank you for everyone that's joined us. We look forward to seeing you on future BYK-Gardner webinars. So thank you, and have a great rest of your day.
Thanks, everybody.